Welcome, students. Today's lesson is about the graphical interpretation of rational functions. Session 1. By the end of this session, you will be able to determine different characteristics of a function, write an equation of a tangent to a curve at a specific point, and represent graphically a polynomial and a rational function. So let's recall some characteristics of a function. The domain of definition is defined by the set of values of x such that f of x is defined. For a polynomial function, the domain of definition are all the possible values for x, from minus infinity to plus infinity with open intervals on both sides. For example, this is a polynomial function, so its domain of definition is from minus infinity to plus infinity with open intervals on both sides. For rational functions, which are represented as fractions, the domain of definition is defined such that the denominator b of x should be different from 0. For example, here's a rational function with x plus 1 as the denominator. So x plus 1 should be different from 0 and x should be not equal to minus 1. So the domain of definition for this rational function are all the possible values for x except minus 1. We write the domain of definition as from minus infinity to minus 1 with open intervals on both sides, union from minus 1 to plus infinity with open intervals on both sides. The limit of a function is the value that f of x approaches as the input x approaches some value. The limit of a function can be either a constant, plus or minus infinity, or be in indeterminate forms. Indeterminate forms include adding plus or minus infinity, dividing infinity by infinity or 0 by 0, and multiplying 0 by infinity. For example, here we want to determine the limit of this function as x tends to 1. We substitute the values of x by 1. The result was 0 divided by 2, which is equal to 0. In the second example, we want to determine the limit of this function as x tends to 1 plus. Similar to the previous example, we need to substitute the values of x by 1. The result was minus 2 divided by 0 plus, which is minus infinity. In this final example, we want to determine the limit of this function as x tends to plus infinity. In such case, we need to take the highest power in the numerator and in the denominator. The highest power in the numerator was x squared, so we take x squared. The highest power in the denominator was also x squared, so we take 2x squared. X squared and x squared cancel each other, and we're left with half as the limit for this function when x tends to plus infinity. The asymptote for a function is the value that the function comes closer and closer but never quite reach. We have three types of asymptotes. A horizontal asymptote that has an equation of y equals to a constant b if and only if the limit of f of x as x tends to plus or minus infinity would be equal to a constant b. A vertical asymptote has an equation of x equals to a constant a if and only if the limit of the function as x tends to a is equal to plus or minus infinity. Finally, we have the oblique asymptotes that has an equation of a straight line y equals to ax plus b. It has a couple of conditions. First, the limit of f of x as x tends to plus or minus infinity should be equal plus or minus infinity. Second, the limit of f of x minus y of d, which is the equation of our straight line, as x tends to plus or minus infinity should be equals to 0. So let's solve an example for horizontal asymptotes. In this example, we have f of x equals to 3x minus x squared over 4 minus x squared. As you remember, the first step is to find the limit of f of x as x tends to plus or minus infinity. To find the limit of f of x as x tends to plus or minus infinity, we need to look at the highest powers in the numerator and denominator. Here, they are minus x squared divided by minus x squared, which is equal to 1. Therefore, y equals to 1 is our horizontal asymptote. Now let's see how it looks on a graph. The red line here, y equals to 1, is our horizontal asymptote. And as you can see, our function comes closer and closer to y equals to 1, but never quite reach it. Now let's solve an example for vertical asymptote. In this example, we have f of x equals to x plus 3 divided by x minus 2. Again, we need to find the limit of f of x as x tends to a constant to be equal to plus or minus infinity. To solve the limit of f of x as x tends to 2, we substitute x by the value of 2. Here we get 5 divided by 0, which is plus or minus infinity. Therefore, x equals to 2 is our vertical asymptote. Now let's look at the graphical representation of this. Here we have the dotted line as x equals to 2. This is our vertical asymptote. And f of x comes closer and closer to our vertical asymptote, but it will never quite reach it. Now let's solve an example for oblique asymptotes. Here we have f of x equals to 2x plus 1 minus 3 divided by x minus 1, and the straight line d of equation y equals to 2x plus 1. Again, we need to look at these two conditions. First, we find the limit of f of x as x tends to plus or minus infinity. The first part of f of x would give us plus or minus infinity. In the second part, we are dividing by plus or minus infinity, so the second part is equals to 0. Plus or minus infinity minus 0 is plus or minus infinity. For the second condition, we need to find the limit of f of x minus d, as x tends to plus or minus infinity. If we want to subtract d from f of x, which is this first part, we'll be left with minus 3 divided by x minus 1. The limit of minus 3 divided by x minus 1 as x tends to plus or minus infinity is equal to 0. So the line y equals to 2x plus 1 is our oblique asymptote. Now let's look at it on a graph. Here we have this line y equals to 2x plus 1, and this is our function in red. Our function will come closer and closer towards the line, the oblique asymptote, but it will never quite reach it. When we talk about the parity of a function, we're mainly dividing it into categories: even, odd, or neither even nor odd. The following applies if the domain of f is centered at 0, where x and minus x both belong to the domain of definition of f. If f of minus x equals to f of x, then f is an even function. An even function admits y prime oy as an axis of symmetry of its curve. Let's solve an example. Here we have f of x equals to x squared minus 3, and its domain is the set of R. F is an even function because x and minus x both belong to the domain of definition of f, and f of minus x equals minus x all squared minus 3, which is the same as x squared minus 3. So f of minus x is equals to f of x. Now let's look at our example and how it looks on a graph. Here we have values for minus x and x. They both have equal value for y. As we move our minus x and x points, we will always have equal value for y. So f of x equals to f of minus x, and our function is even. You can also notice that y prime oy is our axis of symmetry for our curve. The following applies if the domain of f is centered at 0 and x and minus x both belong to the domain of definition for f. If f of minus x equals minus f of x, then f is an odd function. An odd function admits the origin of axis as its center of symmetry. For example, f of x equals to x cubed minus 4 of x, and its domain is the set of R. F is an odd function because x and minus x belong to the domain of definition of f, and f of minus x equals minus x cubed plus 4x, which is the same as minus f of x. Now let's look at our example and how it will look on a graph. Here we have values of minus x and x. Both have equal and opposite values for y. As we move through our x and minus x values, we will always have equal but opposite values for y. So minus f of x equals f of minus x, and our function is odd. You can also notice that the origin of axis is our center of symmetry. The straight line x equals to a is an axis of symmetry of a curve if the domain is centered at a and f of 2a minus x equals f of x. Let's solve an example. Here we have f of x equals to x squared minus 4x plus 1. Its domain is the set of R, and it is centered at 2. X equals to 2 is an axis of symmetry since f of 2a, which is 2 times 2 f of 4 minus x equals to f of x. A point I of abscissa A and ordinate B is a center of symmetry for a curve if the domain is centered at A and f of 2a minus x plus f of x equals to 2b. For example, here we have a function of y equals to 2x minus 1 over x plus 1. Its domain of definition is set for all possible values except minus 1, from minus infinity to minus 1, union minus 1 to plus infinity. I of abscissa minus 1 and ordinate 2 is the center of symmetry for this curve because the domain is centered at minus 1 and f of 2a, which is 2 multiplied by minus 1 minus 2 minus x plus f of x equals to 2 multiplied by 2, which is 4. So let's see our example and how it looks on a graph. Here we have values for minus 2 minus x and x with ordinates b and b prime. As we move through our x values, we will always have I as the midpoint for b and b prime. You can also notice that if we add b and b prime, we will always have a value equals to 4. Finally, I is the center of symmetry for our curve. The derivative of a function is the measure of rate of change for y with respect to the change of the variable x. Here are some functions and their derivatives. It is very important to memorize these in order to solve the derivative for any function. Now let's see some examples. In this example, we have f of x equals to 2x squared minus 3x plus 1. For this example, we'll have to use these four equations. First, we'll notice that this function looks like this one. So we need to find the derivative for the first part and add it to the derivative of the second part and add it to the derivative of the third part. Let's start by 2x squared. The derivative of 2x squared, which is similar to ax to the power n, is an x to the power n minus 1, where a and n are 2's. So the derivative of 2x squared would be equal to 2 times 2 times x to the power 1. For the second part, we have minus 3x. So we need to find the derivative of x, which is 1. The derivative of minus 3x is minus 3. And finally, we have a constant of 1. The derivative of a constant is 0. So the derivative of f of x, f prime of x, equals to 4x minus 3. Let's solve another example. Here we have f of x equals to x minus 1 divided by 2x plus 3. For this example, we'll have to use these three functions. First, you'll notice that f of x looks like u over v. So its derivative would be u prime v minus v prime u over v squared. U prime and v prime are the derivatives for u, the numerator, and v, the denominator. So let's start by u prime. The derivative for the numerator, x minus 1, is 1 minus 0, which is 1. We multiply it by v, the denominator, minus the derivative for the denominator, which is 2, multiplied by u, the numerator, divided by v squared. By simplification, you can get to this answer. Again, it is very important to memorize these rules. As you noticed, most of the time, you'll have to use more than one rule in order to find the derivative for a function. The vertices of a function are the points where the function changes direction. We can find the vertices of a function f by solving the equation f prime equals to 0, where f prime changes its sign. The roots of this equation will be our abscissas for the vertices, and then we need to plug in these abscissas in the equation of f to get their ordinates. Let's see an example. Here we have f of x equals to 3x cubed minus 9x plus 1. Its derivative is 9x squared minus 9. We need to solve for f prime of x equals to 0. The result was x equals to 1 and x equals to minus 1 are the abscissas for our vertices. Then we plug x equals to 1 and x equals to minus 1 in our f of x to get the ordinates. So 1 minus 5 and minus 1, 7 are vertices for f. To draw the table of variation for f, first we need to start by inputting the domain of f from minus infinity to plus infinity with the abscissas for our vertices. Then we need to look at the sign of f prime of x. Since f prime of x is a quadratic function, then we have to input the same sign as the coefficient for x squared on the outer sides and the opposite sign in the inner side. After that, we need to input the limit for f of x as x tends to minus infinity and as x tends to plus infinity. Then we import the ordinates for our abscissas, and finally we need to put the status for f of x. For if f prime of x is positive, then f of x would be increasing. When f prime is negative, f of x would be decreasing. The tangent to a curve at a given point is the straight line that just touches the curve at that point. We need to find the equation of a tangent to the curve of the function at the specific point of c. The formula to be used is y minus y of a equal to f prime of x of a into x minus x of a. Let's solve an example. In this example, we need to find the equation for the tangent, and we have the function f of x equals to 2x squared plus 1, and the point A of abscissa 1 and ordinate 3. So again, we need to go back to the equation. Y minus y of a equals f prime of x of a into x minus x of a. To get the f prime of x of a, we have to find f prime of x. For this example, f prime of x is 4x. F prime of x of a, we substitute x by x of a, which is 1. So f prime of x of a is equals to 4. Then the equation will be y minus y of a, which is 3, equals f prime of x of a, which is 4, into x minus x of a, that is 1. By simplification, we'll get y equals to 4x minus 1 as the equation for our tangent to the curve at point A. Now let's look at our example and how it will look on a graph. The tangent to a curve at a given point is the straight line that just touches the curve at that point. Here we are moving our goal point to reach A of coordinates 1 and 3. The equation of the tangent at this point was y equals to 4x minus 1. Here are the steps to study a rational function. First, you need to determine the domain of definition of the function. Then, determine its limits and the asymptotes. Calculate its derivative and the vertices if they exist. Draw the table of variations and determine some particular points. Finally, you can represent the curve on the system of axes. As a homework, please solve the following questions from your textbook.